just going to have a look at this final case of permutations where instead of arranging things in a line, we're going to arrange things in a circle. What difference does that make? Okay. And it really is down to how many ways you can place the first object. So when we're in a line, okay, so there's all our objects in a line. There's a definite start and a definite finish to a line. So in this particular example here, if I was going to place the object, there's 6 choices we have. But when we come to a circle, and we've still got 6 objects, but there is no definite start and end to a circle. So how many ways can I place the first object? The answer is 1. Because all I can do is put it in the circle. And you might say, oh, no, but there's 6 different positions. But I can rotate the circle. So it doesn't matter where you put it, I can always move it to whatever position I like. Right? So there is no definite start. However, once you place the object in the circle, all the other spots can now be defined. You can say, oh, well, I'm 2 away, or 3 away, or 4 away. Okay. So, in a line, first object, n. Whereas in a circle, first object, 1. But now the object's in a circle, the rest becomes the same. Second object, n minus 1. There's n minus 1 spots left in the circle now. N minus 2, and so on, till we place the last object. So all that's affected is that first object. So in other words, n factorial if it was in a line, but we're dividing it by the number of ways I could have placed the first object, n. Well, that's just n minus 1 factorial. So if we want to arrange things in a circle, instead of doing n factorial, we just do n minus 1. Let's look at some examples. So a meeting room, as people often do when they're holding a meeting, going to sit around the table. It's got 10 chairs. So a committee of 10 people, which includes 3 teenagers in the committee. How many arrangements are there in which all 3 sit together? So we look after the conditions first. Well, okay, the 3 teenagers are going to be together. They can work out their order, 3 factorial. So that's still the same as normal. We haven't actually placed any objects yet. But now, instead of 10 objects, we have our group of 3 plus another 7. So we have 8 objects all up. But we're going to arrange it in a circle, not a line. So it's times 7 factorial. 8 objects in a line, 8 factorial. 8 objects in a circle, 7 factorial. And so that gives us 30,240. All right, we're now going to hold elections for the chairperson and the secretary. Probability that the 2 people that end up being elected are sitting opposite each other. Okay, total ways, no restrictions. So now we've got rid of the restriction about the teenagers being together. So total ways with no restrictions, 9 factorial, 10 people in a circle. Okay, president, well, which is chairperson, suddenly changed their name to president. Okay, president, they can sit anywhere because no one's in the circle yet. So, okay, Mr. President, Mr. Chairperson, whatever you want to call yourself, go sit down. Well, there's one spot, they're just going to sit in the circle. Now the secretary. Well, we want the secretary to be directly opposite the president. So there's only one spot they can go, directly opposite. And then the remaining people. But now it is like a line because there are already 2 people in the circle. So the positions are defined, so we treat it like a line. So 8 people in a line, 8 factorial. So probability, 1 times 1 times 8 factorial over 9 factorial, which cancels down to be 1 in 9. You might remember I said before, sometimes logic works a lot quicker. Think about it. There are 9 seats. Only one of them is going to be opposite the president. So probability that they're sitting opposite, 1 in 9. Let's have a look at another one. This one's from an actual HSC. 7 people now are going around the table. Starts off, how many are possible? So that's just our straight, okay, well, 6 factorial. 7 people in a circle. All right, 2 people, Kevin and Jill, refuse to sit next to each other. How many arrangements are then possible? So we look after the conditions first. Problem is, it's usually easier to work out how many ways they are together and then just subtract that from total number of possibilities, rather than trying to work out all the different ways that they can't be together. So let's work out the number of ways they are together. So they are together. So they're in their group of 2, so 2 factorial ways they could be in their group. We haven't put them in the circle yet, we've just arranged the group. But we now have that group plus another, how many people do we have all up? So plus another 5. So we've got 6 objects. But we're going to place it in a circle, not a line. So it's 5 factorial. 5 factorial. So 2 factorial, 5 factorial, 240. 240 ways. But remember, our question was, how many are they not together? So now we subtract that from our answer in part I, and that'll give us the total number that they're not together, 480. It's just a little flow chart, I guess, to somehow explain the logic behind a problem when you're looking at it, trying to narrow down what technique to use. So, first of all, the key thing is with permutations and combinations is it's without replacements in all these things. So if it's with replacements, then we forget about permutation and combination ideas straight away, and we just go back to the basic counting idea. But if it is without replacement, then, okay, are there restrictions on it or not? So we're going to take into account the restrictions. And if there are restrictions, is the order important? In which case we know it's a permutation. Combination, if the order is unimportant. But if it is a permutation, are we in a line or are we in a circle? Because that will change from n factorial to n minus 1. And then in a line, we looked at, are all the items used? That was just n factorial. Or are some of them used? NPR. But when we looked at ones where we used all of the items, is each item different? Or are some the same? With these other ones, we could still, with this NPR case, have ones where some are the same. But remember, that's where we got to break it down into cases and then add the cases together. They're the little bit trickier ones. All right, 1995, very old question now, isn't it? How long is that? 2021? Woo, 21 years ago. Got a security lock, 8 buttons, and there's a 3-letter code. The reason I like this question, because I think it covered all the different possibilities here. How many different codes are possible if letters can be repeated and their order is important? Now, as soon as they say can be repeated, it's not a permutation, it's not a combination, because it's like with replacement. It's just basic counting idea. So, well, 8 times 8 times 8. 8 for the first number, 8 for the second, letter, so on. So we've got 512 codes. What about they change it? Now that they can't be repeated and the order is important, well, it becomes a permutation now. So it's now a permutation, 8p3, 336. Well, what about now, the way it works is you have to hold all 3 buttons down at once. So that now means the order is not important because you're pushing all 3 down at once. Becomes a combination. So it's now 8c3, 56. All right,